Kale is the bad tasting spinach.
It looks good. Doesn't taste good.
It tastes great. I mean, I like kale anyway. Yeah, I mean, pretty much if you cook anything with any vegetable with a little bit of olive oil and then sprinkle a little bit of salt and a little bit of garlic on top when it's cooked through but not overcooked, you really can't go wrong. And getting the Brussels sprouts at that point is the tricky bit, but you know.
All right, welcome everyone to Tools and Technology Seminar. I think most of you guys have been here before, but in case we have anyone who hasn't, this is just a venue to discuss tools, technologies, methodologies, currently in development, newly developed, or just of use to researchers, maybe used in a novel way. There's a sign-in sheet. It's going around. Please sign in if you haven't already. It's just to help us with the pizza so we can justify continuing to have the pizza. So I'm pleased to present today's speaker, Ian Fox. He is a graduate student in electrical engineering and computer science in Jenna Ween's lab, and we're pleased to have him today.
Hello, and thank you for that introduction. So, I guess when preparing this presentation, I wasn't entirely sure the sort of crowd that I was going to be presenting to. It's nice to see a fairly full room. In particular, I'm going to be talking about methods involving deep learning. And just to get a sort of sense, how many people have heard of deep learning before? Quite popular. How many people have used deep learning or have a good sense of how it works? Okay, so it looks like I pitched this just about right then. I was concerned that you'd all be experts in deep learning, and this would sort of be too level, but it might be good. So my research, I'm a third-year PhD student working with Jenna Ween's, is primarily on applications of representation learning to sequential data. In particular, sequential data derived from healthcare applications, although I also do some work in sports analytics, but it turns out that that's another good way to access some sequential data. Well, I'm going to start off this presentation just by giving an introduction to neural nets. The basic structure of this is going to be, I'm going to talk about sort of what neural nets are and why everybody likes them these days. I'm going to talk about how we actually learn with neural nets. And then I'm going to briefly talk about some of my research in forecasting physiological signals with deep neural nets. First off, we need to think about the sort of fundamental question in machine learning, and that's, how do we represent our data? This is something that people in machine learning have known as the sort of fundamental challenge, and I think AI more generally, basically for as long as the field has existed. It's pretty clear that the difficulty of a problem depends a lot on the representation of the data from which you derive that problem. And in particular, if you have a good, rich set of features that are very discriminative, derived from your data, then it typically is quite easy to learn how to predict various outcomes with that data. As a little example of this, maybe we're interested in classifying pictures as either motorcycles or non-motorcycles. Now, there are a bunch of different ways that, given an image of a motorcycle, we could choose to represent it, right? Here, we're going to focus on just on two-dimensional representations for the sort of ease of visual presentation, but the most natural form of representation for an image, or perhaps the least sophisticated form of representation, would be looking at the pixel values. So here we're looking at 2 pixels, one right there, and we can imagine that these axes represent sort of the intensity of the pixel. This is a grayscale image, or some sort of color combination of those pixels. We have a bunch of examples of motorbikes and non-motorbikes, and we're interested in learning a classifier that will distinguish between the two of them. Now, if we look at this example right here, it's pretty clear that we're going to need a sophisticated classifier. In general, we think about the capacity of a classifier as being a measure of how sophisticated its decision boundary has to be, where I draw some sort of line. It can either be straight or curved or whatever. Everything on one side of the line gets classified as X. Everything on the other side of the line gets classified as Y. As we can see in this example, it's going to be very non-trivial to find a mapping that will sort of adequately distinguish motorcycles and non-motorcycles. And even more concerningly, especially given the sort of low amount of data that we're showing here, it's not at all obvious that a classifier we learn on this training data will generalize to new pictures of motorcycles. Because I could draw a whole bunch of little circles around each of these positive dots, and that'll work perfectly well for my training data. But I don't see from here that there's any guarantee that future points that I sample in this space are going to all fall, within those little circles if they happen to be motorcycles. This is a pretty difficult problem to learn with. Now, if we look at a more sophisticated feature representation, we see that this landscape changes pretty drastically. In particular, here we have two sorts of handcrafted features. Let's just imagine for a second that if I give you a picture of a motorcycle, you can instantly and automatically tell if there's a handle in that motorcycle, or if there's a handle in that picture, maybe of a motorcycle and may not be of a motorcycle, and a wheel in that picture. Now, if I have this sort of more discriminative feature space, maybe this is a probabilistic classification, so this feature demonstrates our probability that a wheel exists, and this demonstrates the probability that a handle exists in that image. Once we cast things into this space, suddenly the problem becomes a lot simpler, right? We saw all of our negative examples are sort of clustered together in one well-defined subset of the space, and all of our positive examples are in another set of the space. That sort of makes sense, We would expect that motorcycles have handles and wheels, and we would expect that things do not have handles and wheels are not motorcycles. So this is, first off, easier to learn with a simple classifier. We see that a single straight line perfectly divides our training and our test set. And we can also sort of intuitively think that because there's such a simple pattern here in this limited subset of the data, we're more likely to get better generalization to new images of motorcycles or not. Of course, in machine learning, we're not always interested in classifying motorcycles or not, but the general structure of our problems is we're given, hopefully large, amounts of complicated data that we don't really want to work with manually, and we want to try to, learn mappings from that data to useful things. And what I just described here, where I said, okay, so we have some sort of handle and a wheel and that sort of intuition there. It's all well and good. Again, for this problem with motorcycles, it's not really what we're interested in. We're interested in general techniques for complicated data. And what I was sort of describing there, this process of handcrafting features for your task, it can be very effective, and it can be very important, and it's been like sort of the cornerstone of most machine learning research prior to, I don't know, maybe the 90s or so. But it requires expert knowledge, so I need to know what a motorcycle is and isn't, first off, beyond just sort of the mappings that are present in the data. I need to have detailed understanding of the anatomy of motorcycles. It can be time-consuming to sort of hand-tune these expert features. Remember, I just said, okay, so you have some automated way to tell if there's a handle in the image, right? But, that could be just as complicated of a task as determining whether or not the thing is a motorcycle or not. Now, as we get sort of further down in the granularity of features, it becomes easier and easier to think of a real, automated rule that can distinguish between those cases, but suddenly we need to worry about building a handle classifier, and with a handle classifier, maybe we need to get a cylinder classifier, and with a cylinder classifier, you need edge classifiers, and we know how to do edge classifiers. From there, maybe you can build up your way, but it's going to take a pretty long time. We don't want to do it. So this process of having to handcraft your features has been argued as one of the major limiting factors in sort of preventing the widespread adoption of machine learning. In that it's just, these systems are very complicated to implement. They often require a tremendous amount of involvement from other people who have a deep amount of understanding in their field. And it's just, in general, it can work for some problems, but it's not really a general purpose solution. And people are more interested in general purpose solutions. And that'll bring us to neural nets, but first I just want to show off a fun little thing here. And this is just like an app, or it's a website you can go. It's called whatdog.net. And this is, probably the greatest triumph of machine learning. I would say it is a website which, given a picture, will tell you what breed of dog it is. That's interesting, right? It's not at all obvious that dogs. They certainly, for a human, it is sometimes easy to tell dog breeds apart. Some of them look pretty similar, right? But in general, it's pretty easy to say, okay, this is a beagle, and we can recognize that it's a beagle in a variety of different poses and lighting conditions, And different features, the beagle might be fat, the beagle might be small, the beagle might be old. Regardless of those different traits, we seem to be able to tell pretty quickly that things are or are not beagles, right? And now our brain is a very complicated thing, and there's all sorts of complicated priors built into the machinery there. But it's not obvious that, with snake identification or anything, there's any pressing concern for our brains to be able to identify beagles, right? I mean, beagles didn't exist before people, right? So there's no real reason why we would have an incentive to be able to recognize beagles. So the fact that we have such an easy time distinguishing dog breeds suggests that in all the sort of complicated stuff that's going on in our visual cortex, we're automatically deriving interesting and useful feature representations for different images. And there's all sorts of, different dog breeds can look very different. And what this is an example of is actually the performance of this system. Now, this system online, it is a deep learning system, so all of this is basically trained just by, I have a bunch of pictures of things that are beagles and a bunch of pictures of things that are miniature schnauzers. I train it, and it can do this sort of multi-class classification. Interestingly, it also has a class of, no dog, because I could presumably give this website any picture, and if I give it a picture of a table, I don't care what dog breed it says that it is, they're all going to be equally wrong, right? Now, the dog breed classification problem is non-trivial. And it's actually a sort of, there's a couple of well-known examples, particularly this one, Chihuahua or Muffin, where you look at these pictures, and if you sort of don't pay attention to it, it can be pretty difficult to figure them out. Now, when you look a little more closely, you can usually tell the difference between Chihuahuas and Muffins, or sheepdogs and mops. But it's just an indication that in order to build systems that really operate well in the visual realm, you need not only to have sort of good intuitive feature representations, but you also need to have pretty sophisticated representations in order to distinguish between some of these things. It's insufficient here to say, okay, I'm going to find 3 large black dots, and if I do that, then I found myself a Chihuahua. Now, I do want to point out that we can make all these grand claims we want about deep learning, and I'm sure if you've read any amount of tech journalism, you've heard it all already. But we're still not exactly at a human-level intelligence yet for most problems. So, given this image, the thing thinks that it's a poodle, and, we can see that there's some reasoning behind that, right? The hair here is, in fact, pretty similar to the fur that you would see on a poodle. And for some other examples, it's maybe a little more puzzling. There's a big thing right now where with all of these representations, you can see very good performance. I mean, you can always see almost perfect training performance. And you can see good performance in a lot of related data. So this network will probably work very well on pictures of dogs. But they can be oddly susceptible to pictures that operate in entirely different regimes of our sort of feature space. Where when we have pictures of politicians instead of dogs, it can be very puzzling things. It's not all clear sort of where it's deriving these judgments from. That's a little fun aside. We should probably actually get to what a neural network is. Now, a neural network, it sounds very biologically inspired, and I think it was indeed, sort of going back to the original formulation. It had some amount of inspiration from biology, but I think that's often a little overplayed. These aren't neurons. They don't behave like neurons do. Really, what a neural net is, or people might call them multi-layer perceptrons, or people might call them, various other things. But what these are, essentially, are compositions of linear classifiers with nonlinearities applied between the nonlinear classifiers. Now, what do I mean by that? So here we have a one-layer neural net, and it's composed of 3 different parts. The input layer, where we're actually sort of sticking in our picture of a dog. This hidden layer, where we derive a representation from that image. And then the output layer, where we use that representation to make a classification decision. How does this work? It's pretty simple, actually. At the input layer, and you'll notice that I've added in a little bias term to that input layer here. This is just to sort of ease the presentation here. You might also think of there's no actual +1 node here, but each of these weight connections carries with it a separate bias term. Basically, every one of these nodes, this would be Z1, Z2, Z3, is deriving a linear function. And right now I'm not talking about training this, I'm just talking about sort of running through what we would say a forward pass of the network is, just using our trained network in order to make a classification. So each of these intermediate nodes computes a linear function, a linear combination of the inputs, right? So we've got some weight times x1 plus some weight times x2 plus some bias term. And then on top of that, it computes some sort of nonlinearity. So here, I've derived some sort of value from this linear combination, and then I'll do something like apply a sigmoid to that value, or any form of nonlinear squashing function. I don't always need to be squashing functions. In fact, the most popular thing used right now is something called a rectified linear unit, which is a very fancy way of saying you take the max of 0 and the value. So you just, if your value is negative, then you just wipe it out. And the idea is that we want these nonlinearities to be differentiable or subdifferentiable. So we want to be able to define a derivative of this nonlinearity. Once we've got that, we have from each of these nonlinearities and these sort of what we might call, I guess, these H's or activations, the hidden unit activations, and these get passed through to our output. And our output layer is actually just another linear combination. We take a linear combination of these different activations, again with another bias. We might apply some sort of nonlinearity on top of that, and that's the output of our neural network. That's all that a neural network is. It's very simple. The idea is just we have this composition, a bunch of linear functions with nonlinearities between them. Now what I'm showing is something called a single layer, fully connected neural net. We can add in additional layers, and just by adding in more sort of layers of these hidden units. And they will operate just like this layer right here, except they will take as input the activations from the previous layer of hidden units. And this idea of composing all of these different layers together provides some of the justification for our use of this nonlinearity here. If we didn't add in that nonlinearity, we'd just be basically composing compositions of linear functions, which is, of course, just another linear function. So that wouldn't be very interesting. Now, there's a whole bunch of interesting results on just these sorts of shallow and simple fully connected networks. Maybe most notably, a single layer hidden neural net with an arbitrarily large hidden layer, so we process a whole bunch of hidden units, is a universal function approximator. So I can train it to arbitrarily closely approximate any function that you might wish. And these fully connected neural nets, we can have sort of fancier versions like convolutional neural nets, recurrent neural nets, but those are all sort of just dressing on it. And they're all derived identically to this very simple case, just from simple combinations of simple linear functions. You get a whole bunch of those, and that's sort of where the magic happens. One way to think about what's going on here, as I said, I've sort of motivated this all by a representation learning perspective, is that what we're doing is learning a representation with this hidden layer, which is then used by our final output layer. There's been a lot of work, so a lot of tangential work in different branches of machine learning about what's the best way to learn with data. The approach taken by the deep learning community is that you shouldn't focus at all on how complicated your decision boundary is when you're actually classifying your data. All of your work should be in learning a representation for your data. Because really what we're doing here is we're saying, okay, we are going to use the simplest possible classification scheme. We're going to just define a linear function and use that linear function to classify our data. And all of our sophistication goes into how we're going to represent our data. And the real genius of deep learning is trying to automatically learn discriminative feature representations just from data. So we remove that handcrafting expert step. Yeah, so we can think about this. This phi here is something that you might see if you're used to working with kernels or things like that. It's just a way of saying we have a raw input representation x. This phi gives us a representation of that x, which we're going to learn with. And here, that representation is the intermediate hidden units there. Now we've got ourselves a little bit of an example. So I'm sort of making all these hand-wavy claims about learning representations and things like that. And it's sometimes useful to ground yourself in reality. Here we've got ourselves a very simple binary classification problem. Not too simple, right? I mean, we see here we've got all of our negative cases and all of our positive cases. And there's no one line, there's no linear classifier, which is going to do perfectly in separating our training data, right? But we want this to be linearly separable, because that's sort of the whole idea. We want to get a representation where it is easiest to discriminate. And we can do that using a neural net. So here we've got two neurons, this Z1 and Z2, and our nonlinearity is that rectified linear unit that I was talking about earlier, where we just take the maximum of 0 in our activation. And the question is, how can we use this representation in order to sort of cast this, or how can we use this setting to cast this into a representation where everything is linearly separable? If you just look at it, it sort of becomes clear what the answer is, because we have these two lines sort of already drawn in, defined by Z1 and Z2. Each of these are just the the zero line of our linear, sort of the hyperplane defined around each of these neurons, and we see the positive direction here and the positive direction there. And then once we sort of look at this and we think about how this will look in this plot, well, it becomes clear that it's going to be linearly separable. I just want to take some time now, just think about, what do you think this is going to look like cast into this this new representation? If you all have a hypothesis, here we go. There we go. So what we can see is that because we have our two dimensions defined by this activation on Z1 and Z2, and the positive direction of this hyperplane is in that direction, the positive direction in this hyperplane is that direction, that means everything in this space is going to be negative in those dimensions, and also, every point over here is going to be negative with respect to this dimension, every point over here is going to be negative with respect to that dimension, but our nonlinearity takes care of that and just says we're just going to be 0. So basically what we're doing is just casting all of this data, just doing a projection onto this basis here, and we can see, of course, all of our negative data is going to be precisely at 0, 0. It's pretty simple to draw a line that will perfectly separate that data. So here's just a very small, concrete example of how we can learn better representations of data. Now, that's all well and good, right? So I've sort of hopefully motivated that neural nets are something that are interesting and worth thinking about. There's a big problem, right? I sort of started all of that by saying, okay, we've got this trained neural net. We've got this neural net which defines these two boundaries. I mean, how is that any different from handcrafted feature designs? Well, the answer is that the difference is we don't need to assume that we have, that we're given that neural net. We can learn that neural net automatically from the data. There's a bunch of different ways that you can do this. There's a whole bunch of interest in maybe biologically plausible mechanisms of training these things, or recirculatory methods of training these things. But it turns out that none of those really work as well as a very simple technique developed in the 1970s, I think, called backpropagation. Backpropagation, it's probably what most GPUs that aren't working on mining cryptocurrency are doing most of the time, or at least when they're doing machine learning. They might also be, playing video games or something. But it's a very, very, very widely used technique, and it's also quite simple to understand. There's nothing sophisticated going on here. And that's maybe a theme running throughout deep learning is very little of deep learning is sophisticated from a human engineering perspective. And that's hopefully the elegance of it, right? That we don't need to be geniuses to understand what's going on here. We just let the data sort of speak for itself, and that will hopefully result in something good. Here we just have a little example of optimization, because the idea is we're going to start off with some sort of predefined architecture for our neural net, and then we're going to optimize the weights of that neural net in order, on some sort of training data in order to achieve maximal performance. Now, what's the simplest mechanism of optimizing? Well, I guess the simplest would be 0th order optimizing, just picking random points, seeing how well you're doing, and then reporting the best one. But that's not super interesting. Because we have a system, remember that we sort of took care to make sure that all of our nonlinear functions, our sort of activation functions there, were differentiable or subdifferentiable, and all of the linear combinations are, of course, also differentiable. We will have a differentiable manifold, or at least a subdifferentiable manifold, on which we can work. And once we have that, that basically means that we can think of things sort of in this hill analogy, right? Things are more or less smooth, and so we can just use, some form of gradient descent in order to optimize. The idea of gradient descent being, if I'm standing in the dark on a hill, I can see maybe a little bit out in front of me in any direction. If I want to get down to the bottom of the hill as fast as possible, I just follow the direction of steepest descent, right? That's all we're going to do here. So we just, we'll find the gradient with respect to the weights of our neural net on our output, and then we update our weights taking some small little step. I know that sort of step size can be important because if I'm in the dark on some sort of hill, maybe I've got very long legs or something, I could take tremendously long steps. But since I only have a sort of limited view of my world, I don't really want to go super far, because it could be the case that the lowest point is actually just a few feet in front of me. If I take a very long step, I could be suddenly, even higher than I was to start off with. So we're going to be doing some form of gradient descent optimization. Again, the idea of gradient descent is we have some sort of function with respect to inputs. We take the derivative of that function with respect to the inputs. And that's just sort of how we define the derivative. And then we're going to move in a direction such that we are minimizing it, right? Because the gradient will give us the slope. There are a couple of different ways that you can take gradients, right? And you can do a numerical approximation, which is sort of what we're getting at here. Or you can take analytic gradients. You typically want to take analytic gradients because numerical gradients are very slow, and you're going to have to do a lot of work already to optimize neural nets by back propagation, so you don't want to really do the numerical approximation. Now, before we go much further, I just want to talk a little bit about computational graphs. A computational graph is how we organize sort of all of our thinking about neural nets, the different components of neural nets, and it's much more general than neural nets as well, right? A computational graph is just a manner in which we can sort of organize a series of operations that we're performing on some form of data. So here we've got a computational graph, which is defining, actually this one doesn't really define much at all, but we've got one up here, yeah. So here we've got a computational graph defining this function here. And these slides are just to sort of make a point that what I'm about to go through, so these computational graphs, we just sort of divide any form of computation into a bunch of simple sequential steps. It can be used to represent a lot of very complicated things. And before I was talking about a single layer hidden net, that's very simple. You've got this thing called AlexNet. This was maybe what kicked off the current boom in deep learning, where this architecture, which sort of ironically in every image of it is cut off part of it. It's something you notice. It's just like every copy of this is cut off. I don't know why.
Because it was copied.
Yeah, it was all copied. I think in the original paper they had to cut it down to get it to fit in the page limit, so I don't know. Pretty silly, but this convolutional neural network structure was really revolutionary in that it demonstrated a tremendous improvement in performance on a very important computer vision problem called ImageNet. And if you're interested in that sort of stuff, we actually have one of the professors here in the Geeks department. Yeah, Xiaodong. He was the creator of ImageNet.
Started.
Yeah, so pretty exciting.
Very exciting.
Not only that, but we can get computational graphs for these fiendishly complicated things that haven't really been demonstrated to work super well yet, called neural Turing machines. And the idea here is you want to create a super general neural net that essentially operates as a computer. It's sort of Turing complete. Now there are other there are simpler architectures which are technically Turing complete or can simulate Turing complete operations, but neural Turing machines are a sort of more direct form of that. And they're these stateful things, so you run them thousands and thousands of times on different problems, but their whole operation can be encoded as a computational graph.
So why is it called neural?
A neural Turing machine?
Just because it's a neural.
Yeah, because it's a neural net, or it's derived from a neural net. And why are they called neural nets? Because people had sort of more grandiose biological visions back when these things were getting codified. Here we're going to talk about performing backpropagation on a somewhat simpler computational graph than this, because we only got so much time. Here we've got a computational graph which is defining the operation z times x plus y, right? Pretty simple operation. We have three inputs, x, y, and z. We take x and y, we add them together. So minus 2 and 5, here's our particular example. We have 3. Then we multiply them together with this z, which is minus 4, and we get minus 12. That equals f, right? So if we want to take the derivative of f with respect to x, y, and z, how can we do that? Well, first off, we might observe that it could be useful to define this intermediate node here, this addition, has its own sort of unique property, or its own sort of named entity, q. Q is equal to x plus y, right? So if we want to think about the derivative of q with respect to x, it's just going to be 1. Derivative of q with respect to y, it's just equal to 1, right? Hopefully I'm not blowing anyone's mind here. And f is q times z. The derivative of f with respect to q is z. The derivative of f with respect to z is q. So that's good. We've derived a whole bunch of different derivatives here. We have a whole bunch of different values.
The total differential. I remember teaching.
Yeah, it's all so simple. This is just the chain rule that I'm going to be showing you, and that's the revolutionary backpropagation algorithm.
Exactly.
So if we just want to sort of keep a store of the errors here, and this keeping a store is going to be important. I'll explain why in a bit. We then go in, we sort of fill in. So we have this 1 here as our sort of gradient value. We fill in that derivative of f with respect to z that we calculated earlier. Q is 3, remember, so that's 3. Now you want to update the gradient for q. Well, it's going to be 1 times the derivative with respect to q, which is z, and remember, z is minus 4. So and hopefully you're seeing that all of that what I'm doing here is just sort of shuffling numbers around. Nothing fancy going on here at all. Derivative of f with respect to y. Oh, what's the derivative of f with respect to y? We can use the chain rule to find that, right? And that's just, this is back from Calc 1 days, right? The derivative of a function with respect to some sort of second level input is just the intermediate derivative times that local derivative. Easy as 1, 2, 3, right? And we have the derivative of f with respect to q. We have the derivative of q with respect to y. So that means that we have the derivative of f with respect to y, and we just sort of plug it in, minus 4, right? Similarly for z, minus 4, and there we have it. We now have the derivatives of the input with respect to the output, and if we want to minimize this, now maybe it doesn't make so much sense to talk about minimizing this function, because pretty clearly we can minimize it indefinitely, right? Just take z to be some arbitrarily large negative number, and take the x and y to be arbitrarily large positive numbers, or something like that. But if we were operating in some sort of constrained field, and there are various ways in which this might be more sensible. But this is just how we can do backpropagation on our computational graph. And the real key with backpropagation, the idea that we can use our inputs and we sort of take the chain rule to eventually derive the outputs, that's completely obvious. That's something that sort of people have known since people knew about the chain rule, right? And what backpropagation is saying is just, okay, well, we want to, it's essentially dynamic programming. We want to sort of fill in from the back first so that we don't have to recompute, say, the derivative of q or the derivative of f with respect to q multiple times, which we would have to do if we were doing this sort of in the naive forward manner. And in general, if we've got some sort of differentiable function here, and we want to backpropagate gradient through that, all we do is we first figure out what the local gradient is, the derivative of x with respect to our function here, or the derivative of the function with respect to x, and the derivative of the function with respect to y. We look at the incoming gradient, so the derivative here, that L is representative of our loss, which is sort of the final output of our network. And we take the derivative of our loss with respect to this input, which is very easy to do, sort of going back to this example here, if we've already pre-computed everything in the chain rule, right? So if we've already pre-computed this thing, that's pretty simple. And then just use the chain rule again, sort of to pop it out the back. So we will compose the local gradient with the sort of global gradient, and there we go. We have the gradient flowing backwards from this net. And importantly, we can see this doesn't need to be the sort of input layer here. This can be any node anywhere in your neural net. And I don't care if this is, this could be the sort of linear layers that I was talking about earlier, the fully connected net. This could be some sort of convolutional filter. This could be some sort of recurrent thing. So long as I can, so long as these elements are well defined, doesn't matter what this function is, right? I can pass the gradient on through. That's why this is such a general thing. So once we do that, I hope I've convinced you now that we can find the gradient of weights with respect to some sort of output loss. And once we have that gradient, again, then it's just gradient descent. We have that gradient. We take a small step in the direction of that gradient, and then we go back and do everything all over again, right? Now there are a whole bunch of different people talk about different sophisticated optimization schemes. There are things like adaptive learning rates or adaptive step sizes. There's a whole lot of pretty sophisticated stuff, but interestingly, recently there's been a good deal of evidence that nothing much really beats simple gradient descent or stochastic gradient descent. I will say so people rarely do what's known as full gradient or batch gradient descent, where you find the derivative of your weights with respect to the full input, because typically, hopefully, the data that you're learning with is massive, and so you can't fit all of your data into memory, let alone compute the gradients on it. So you'll take sort of the derivative with respect to subsets, or mini batch gradient descent, stochastic gradient descent, things like that. So now I want to talk a little bit about my particular interest in deep learning. So deep learning, very useful, very general, very exciting, I think. And I'm using it for physiological time series forecasting. In particular, I'm looking at forecasting blood glucose data. So this is collected from people with type 1 diabetes. Type 1 diabetes is basically just when your pancreas is not producing insulin. It's fairly common, and diabetes on the whole, which also comprises type 2 diabetes and like gestational diabetes and things like that. Diabetes is the 7th leading cause of death, and there are more than 100 million Americans who are diabetic or pre-diabetic. So I think a pretty, when I first saw that, I thought there must be some typo. I was like, I can't believe that. 1 in 3? Yeah, so it's pretty remarkable. Now, luckily, diabetes is not the death sentence that it once was, in particular type 1 diabetes, in that with the application of insulin, you can usually control your blood glucose. There's a lot of very strong evidence that tight control of blood glucose values to between, I think, around 140 and 70 milligrams per deciliter of blood. That's just a measurement of blood glucose. If you can keep your blood glucose in that range most of the time, then you are much less likely to have a lot of the various negative outcomes that are associated with diabetes. Unfortunately, it can be kind of difficult to keep your blood glucose under control all the time. A big thing that people are interested in, then, is the development of some sort of artificial external control loop that will sort of manage your blood glucose values for you. An artificial pancreas is what it's called. And a component of the artificial pancreas, sort of narrowing down further and further into my research, component of the artificial pancreas would be a good model for predicting the action of blood glucose. So if you know what the future of the blood glucose signal is going to be, then you can take better actions to try to prevent that future if it's going to be something bad, like a spike in blood glucose. So the basic task that I'm having here is a time series forecasting task. We have some sort of signal that is the input to our model. The output of our model is our predicted guess for what future values in that signal might be. And the error or the loss that we're going to be training to and trying to minimize is the difference between our prediction and the actual outcome of that. Now here's a somewhat standard forecasting framework. It's something that I'm sort of building off of here, where the idea is that we've sort of inherent in this model is there's a whole bunch of other stuff which is looking at previous times in our signal down to whatever time we're interested in. But when it comes time to actually making a prediction, we'll use our input. We'll put that through some sort of model. Here I've been using a variant of a recurrent neural net, which is just a neural net that has some sort of notion of state which persists between predictions, useful for sequence-level tasks. That neural net learns some sort of representation. That goes to our little output layer, some sort of simple linear classification scheme. And the output of that is, hopefully, the next value in our sequence. Now, if we want to, here, we might not be interested in forecasting only one step in the future. We might want to forecast multiple steps in the future. So to do that, we'll take our prediction of sort of the next step in the sequence, and we'll feed that back into our model, right? So we have our prediction, we feed that in, we get the prediction of the next time step, feed that in, get a prediction of the next time step. All good, right? So we've got this. Well, here, I'm not really showing it off, but this is a deep neural net predicting blood glucose values. It's going to do fantastic, right? Maybe not so much so. I'm comparing it against another perfectly reasonable machine learning technique called random forest. I'm using a random forest to regress versus this sort of recursive formulation of blood glucose forecasting. I'm looking at a large data set of real blood glucose data collected from individuals with type 1 diabetes. And what we see is that on all the data, we actually perform a little bit worse. I should put this in here. This is mean squared error of our sort of forecast versus the actual the actual value. And this is sort of summed over 6 different steps, so we're predicting within this 30-minute time horizon. And we see that our recursive neural net actually isn't doing as well as a simple random forest. Although encouragingly, on this sort of subset of the data, the event subset of the data, which represents periods where you have sort of larger variations in blood glucose levels, and is actually sort of the subset of the data that we maybe most care about, we see a pretty big improvement in performance. So that's maybe encouraging, right? But still, not so great. Since I just spent such a long time sort of waxing poetic about the powers of deep learning, it's sort of disconcerting that we're not seeing a commanding improvement. And maybe that's a common thing in machine learning. There's a lot of things which are philosophically appealing, but don't always get big bangs. Although I'm going to show that there are ways that we can correct this a little bit. One issue here with this sort of recursive forecasting framework is the idea of error accumulation. And it's something that's well known in sequence modeling tasks where if I'm using a sequence if I'm using a prediction of a sequence as input for that sequence, there can be a big issue where when this model was trained, it was used to all of these guys being actual observations. It was used to these things being correct. And so it doesn't really know how to recover from the errors that it makes. Because if it makes some error here, that error is automatically corrected at training when we feed in the real next value of the sequence. Whereas here, it makes some sort of error. So you can imagine you get very good performance forecasting sort of one step at a time, right? If you're always given the real next value, even if you're consistently slightly biased above the real value. But when you do this recursive formulation, predicting multiple steps in the future, those small biases add up more and more, until eventually you wind up with pretty poor performance. So I was looking at a multi-output forecasting framework for deep neural nets, and there's a bunch of different ways that you can do that. So one of the ways, I've sort of removed all of these states here, but you can imagine they're still there, actually. I'm just sort of focusing on one at a time. Instead of having a single output at each node predicting the next time step, we can have multiple outputs predicting multiple steps in the future simultaneously. So now at training, we're forcing our model to learn a more consistent estimate of the dynamics of the signal, because if it's consistently biased, slightly upward sort of at each time step, then we sort of see here when we get to that final one that, oh man, we've gone way off, we need to correct that. Whereas you don't see that with the recursive forecasting framework. We also can have modifications. So if we have this, where we're sort of independently decoding our hidden state into a bunch of future predictions, it could well be the case that we'll see a large amount of variation on these outputs. And for example, if I'm predicting a spike in maybe this little segment of the output, there's no way that the network will know inherently, because especially if these decoders are trained separately, that spike is occurring, so it knows to sort of predict the continuation of that spike at future points in the prediction. And we can ease that restriction just by allowing the nodes to communicate with each other in some way. So like here, we make a prediction at time +1. We use that prediction plus information from here to predict time +2, and then so on. We're developing a technique which I think is pretty interesting, where we're taking a slightly different approach. Instead of operating in some sort of time prediction scheme where inherently, it's harder to predict the future as it gets further and further ahead. That's pretty much universally true, right? Because entropy increases and all of that. The error of time only goes one way. So what if instead of trying to sort of sequentially predict the future further and further, where we're sort of guaranteed to get accumulating errors in one form or another, we try to predict a function which generates the future. Now, if we assume that this function sort of locally approximates the signal well, then it could be the case that by sort of predicting sequentially instead of observations, parameters for this function which is generating the sequence, we could get around, or we could at least disentangle the issues of the future being more difficult to predict and sort of sequences being more difficult to predict as you predict out this sort of error accumulation that I was talking about before. We could try to disentangle that somewhat. Now, of course, there's no free lunch anywhere. This only works if we assume that whatever function class we're estimating parameters for accurately models the future, and it will only ever accurately model the future to some time horizon, right? Because the future becomes harder and harder to predict, more chaotic. What we saw with these different techniques, I guess I should have named them. This, I call it a baseline multi-output. This is an autoregressive multi-output. And here we're assuming this function is some sort of polynomial, and so this is a polynomial multi-output method. We found that these approaches tended to do fairly well We see, in particular, the baseline multi-output gets a big improvement in predicting these sort of normal cases while maintaining good performance in the event cases. And we saw sort of further improvements with the autoregressive thing, although it didn't do terribly well in the event. Similarly with the polynomial prediction. Although interestingly, so although these two methods, neither of them really crushed the baseline multi-output method on either of our data sets. First off, I left off a few other sub-data sets because things get a little complicated, which they might have done better on. Tough to say. Things get kind of small. But interestingly, when we look at, mostly people don't use individual models for prediction, they use ensembles of models. When we look at an ensemble, it turns out to be very important to include these different things. So they seem to be capturing some important elements of the dynamics of the sequence. And I should say these are, so if we remove these guys, train a couple of different baseline multi-output things so that they're different, we ensemble all of those together, we get worse performance than we do when we ensemble all these different sort of multi-output methods together. And together, their ensemble does, in fact, beat the random forest pretty convincingly in both tasks. So that's nice, right? We've demonstrated that deep learning does, in fact, have some amount of promise. And also, this is just a sort of final result that I had. I was talking about error accumulation, right, here, but I never really backed that up with data. And here's just seeing the root of the sort of median squared error of our prediction by the place in the prediction window, where I'm saying I'm predicting 30 minutes in the future at 5-minute intervals. So this is predicting 5 minutes in the future, 10 minutes, 15, and so on. And we see the error by all of our different methods. All we see is for all of the methods, actually, the error does increase over time, because again, there's really no way to avoid that. But interestingly, all of our multi-output methods, they tend to have a decreasing rate of error accumulation relative to the recursive. So actually, I showed here that we're getting much better performance. But really, if you look at, the predicting 5 minutes in the future, we're actually doing worse than with the recursive forecast. The recursive forecast was learning a better 5-minute forecast. It's just that all of these guys are learning much better, say, 30-minute forecasts. So I thought that was sort of interesting. And that's all the slides that I have. Thank you for sort of humoring me throughout this diatribe about deep learning.
Well, Ian, can you go from that to the graph that you showed to show the improvement in the reduction of the error? Go back to your diabetes graph, where you showed the, that one. Yeah. So what does that combined model do to that error?
So, let's see. I think, I don't know that I looked at this particular.
That'd be a good thing to do.
Yeah. Typically what we see.
One model, and then you combine the models to get a lower error. You should go back and see how it does. 6 steps down. Yeah.
So we're sort of preparing a paper for this work. In that, there are cases. I will say, there are cases. It's not the event that our combined model is a much better forecaster for all time series. For all these blood glucose highs. It could very well be the case. I think this forecast was generated by the random forest, which tends to have pretty low rate of response in its change, which is why we see it has pretty bad performance in these sort of faster changing paces, but maybe why it gets reasonable enough performance, whereas the recursive is more willing to predict drastic changes.
So if you have a baseline predictor which predict that the blood glucose does not change, it will perform similarly as the random forest.
So we looked at that, and we did find that the random forest beat it out by a little bit, but not by a tremendous amount. I think that the mean squared error of just predicting the sort of past as the future values, it was something like 95 or maybe 100 on the full data set. There are cases where the random forest will be able to sort of interpolate out linear trends pretty effectively. So if you see that your blood glucose is sort of inching up, then the random forest will continue that prediction. It's not always going to be a completely flat line. Yeah, it's a good point.
So if you use other extrapolation method instead of machine learning, will you get similar or worse result?
So we also tried an extrapolation method. And what we found is the extrapolation method performed much worse than just predicting the past values, because blood glucose tends to have these sorts of sharp peaks and rises and falls. And if you just do an extrapolation approach over a window which is small enough that you tend to see sort of meaningful slopes and not just always predicting the same value anyway, more or less, what you'll see is that it'll get tricked occasionally by these sorts of peaks, and it'll go off and predict these outrageous values, and so incur massive error.
Is that prediction based on like one individual?
Well, so these predictions, these models,
you've got some input data, right?
Mhm.
You've got some readings. You're trying to predict the future.
Mhm.
So when you graph this, was that like from one person, or is this made up, or what?
So this is I think this is data from one of the people. Or this is one of our little subsets of data from one person.
Do different people have different things going on? And how they are responding over time?
Yeah, so that's that's a very interesting question.
Does that confuse things as to making predictions because there's no typical person?
Mm-hmm. So there is certainly, I guess what we would say, interpatient variability or interperson variability in the glucoregulatory system. Although it tends to be less drastic than just variation that you might observe within someone's glucose signal throughout the day anyway, because sort of no matter who you are, the sort of glycemic peaks and trials that you might fall to might be a little different, and the rates in which you rise and fall might be different. But the primary driver is going to be sort of external phenomena. So like if I have 100 grams of carbohydrates and I'm a type 1 diabetic, it doesn't matter who I am. You're still going to see a sharp increase in glucose value unless you take the right amount of insulin to prevent that.
Yeah. That's a true statement.
There's a question.
Okay.
Insulin pumps,
Mhm.
maybe with some sort of monitoring device, also use similar models. Yeah, that's a good question.
Yeah.
How do insulin pumps make the predictions?
So, it's somewhat proprietary. There are some insulin pump manufacturers that have like open source models. Typically, things are done more with a control perspective. Which, what's the difference between machine learning and control theory? What department you're in, basically. But typically insulin pumps will operate based off of mechanisms like sort of proportional integrative derivative controllers or those sorts of things. A little bit outside of my area of expertise. We did compare our method against, so I will say that the random forest, we're not just sort of randomly choosing a model to compare against, we're choosing a random forest because previous research has demonstrated that that's the most effective sort of standard machine learning model in predicting blood glucose values, and so that's sort of why we chose it for this particular problem. But yeah, most insulin pumps, to my knowledge, do not use highly sophisticated models for predicting future blood glucose values. Now, that doesn't mean that they don't work well. Again, as we sort of see here, you can get, this is maybe not unreasonable performance, you can get pretty reasonable performance in predicting these sorts of things just with very simple models. And with an extrapolation, there's also an interesting thing, right, where here I'm presenting mean squared error. That's not actually really the error metric we care about, right? Because if I'm a patient with diabetes, I don't care if you're saying my blood glucose is going to be 10 points higher than it actually is if I'm well within a normal blood glucose level anyway. What I care about is, do you issue predictive alerts well? Or does the insulin pump sort of operate appropriately in administering insulin during times when I actually need it? So, can it recognize that I'm heading towards a crash of blood glucose values and alert me sort of preemptively to have some carbohydrates, or can it tell that I'm well on my way to a glycemic spike and administer insulin appropriately? Now, for insulin pumps, that's actually somewhat of an easier problem, because if you're sort of looking at hypo versus hyperglycemic or low and high blood glucose prediction, it tends to be much easier to predict periods of hyperglycemia because they tend to be much more stable. So if I become hyperglycemic, it's very rare that I'll be hyperglycemic for some short period of time. I'll sort of creep up into hyperglycemia and then stay there for a while and then maybe come back down, especially if someone gives me insulin. And so that's the main task which the insulin pump is interested in, because it wants to say, well, when you're at that pretty high level, let's start bringing you back down with insulin. And so that's somewhat easier. With hypoglycemia, it's a bit trickier because the damage done by hypoglycemia is much more rapid. And that if you're really hypoglycemic, you start feeling dizzy, you can fall unconscious, you can go into a coma or die if it's particularly severe pretty quickly. And so with hyperglycemia, if I'm just monitoring your current blood glucose, if I even don't really predict the future at all, you can still get a benefit just from being able to detect hyperglycemia and right away start administering insulin, as opposed to waiting for the person to do a manual blood measurement. With hypoglycemia, there's, I think, maybe a bit more interest in sophisticated predictive models. Although, to be fair, it's best to not go into hyperglycemia at all. So if we could use a sophisticated predictive model and prevent that altogether, hey, that's still a win. Yeah?
So recent results and what seems like similar to what you're doing in sequencing coding kind of point out that the most effective to-the-day architectures are these combinations of, the local encoder and some couple of convolutional layers, LSTM, and some attention on the top of the whole things like WaveNet or Tacotron. Those architectures are doing these kind of things. So does your data allow, or did you try any of these approaches that's more of the state of the art today?
Yeah, so WaveNet is an interesting architecture. That's something that I'm working on with some other related stuff with blood glucose and in general representation learning. But WaveNet is also, so it's a very cool result. It's also a somewhat simple result, right? In that all that WaveNet's doing is looking at sort of a dilated causal convolutional neural net. Basically, it's a convolutional neural net where you spaced out your convolutional filters. That might not mean anything to people who don't know what a convolutional layer is, but it's nothing super fancy. What's interesting about it is just that, I think one of the most interesting things about it is that it's really, and this is sort of maybe a bit of a tangent, but I'm very interested in forecasting not just for sort of clinical applications, but also as a representation learning thing, because if I'm trying to learn a representation of a sequence, I think that forecasting is a mechanism of self-supervision to learn a representation of that sequence, which is going to be particularly effective, as opposed to sort of standard methods of just sort of reconstructing a sequence, like an autoencoder or something like that. And I think that a lot of the gain that you're seeing in WaveNet is because it is inherently using forecasting as a representation learning tool. In that a lot of what they're doing with WaveNet is conditional decoding. So they're not interested in sort of raw forecasting, but in using a sophisticated representation of sort of speech signals in order to construct mappings between actual sort of characters and those signals. That's maybe a bit aside.
If you looked at the Kalman filter, you compared that.
Yeah, so we tried working with the Kalman filter on this data. We were never able to get it to generate particularly reasonable results, and I don't think we ever found in sort of several days of tinkering that we could get results that sort of came close to the random forest performance. And other people have done maybe more thorough comparisons of Kalman filters to random forests and found that random forests tend to win out.
It might be good to add that in combination.
Yeah, certainly. I mean, that's
because it gives you it creates a space. This is fantastic site that I just filled up that shows how the Kalman filter works. Just type Kalman filter and say, how does Kalman filter work? And this is just a absolutely cool site that shows how it works in pictures. It's quite informative. I used it years ago, and it might be
yeah, maybe. It can, even models that don't have particularly good performance in and of themselves can be very useful in ensembling, so long as the ways in which they make mistakes are corrected by other models in the ensemble, right?
Exactly. And this would add more diversity, because really, if you think about it in this model ensemble approach, you want diversity. And I think the Kalman filter could help you drive down results. Well, look, I think people are leaving, so that's really great. Did a nice job.
Thanks, everybody, for bearing with me here. I hope that you learned something about deep learning. I hope that now, you can go out and sort of impress everybody with your knowledge. So yeah, I know what a deep neural net is. I can train them. And you can train them. If you have a large amount of data, maybe try deep learning. It's fun. It's not always easy. It can be easy. If you're working with natural images, it can be quite easy. Yeah. And it's what's generated the most promising results recently in machine learning across a range of different tasks. So, thank you.
Thank you.
You're in